Now, we've only got two things left to learn this in December. One of them we've kind of talked about briefly a little bit that we'll talk about today, derivatives and graphs and learning things from that. This is a big part, well, this is a part of calculus, is being able to not just do the algebra side, which we think of as math, but also be able to look at graphs and determine things from graphs, especially looking at the derivatives and determining things from it. And that's what we're going to talk about some today. And tomorrow, we will talk about L'Hopital's rule, and you'll get some idea of why I think you'll probably like L'Hopital's rule. It makes life a little bit easier for you in certain things. And then to have a little test next week, and then have a little exam the following week. All you need to know for the exam is everything. So let's talk about, also assignments. I sent you out the email. You've only got 2 homework assignments, I think, a WebAssign and 4 FRQs along with the test. So that's over the next couple of weeks. You don't have any homework due tonight, so I would strongly encourage you to go ahead and get started on those FRQs. I know that you're going to be slammed with everything over the next 2 weeks, and the stress level is going to go up. You've got to go ahead and plan for that and begin working on some things a little bit earlier. So today, we're talking about 25 derivatives and their graphs. And I want you to just read the instructions there. The graph of the derivative f, the derivative of f, which is f prime, is given. So that's the derivative graph. It's not the function, it's the derivative of it. From what you've got in front of you, determine all the critical points, the inflection points, the intervals of increasing and decreasing. All of this is about the function. The intervals where the function's concave up, concave down, where the derivative is positive, where the derivative is negative, the maxima and the minima. That's a bunch of things that you can figure out from that. So I want you to just take a moment, think about it, and somebody tell us how you think, how you would start. There's lots of different ways you can approach this. Yes, sir.
I would first mark the place where it crosses where it goes to 0 as R.
Which are what? All right.
2, 4, and 0.
All right. So Wesley says he's going to start off with these 3 points here, and he says that all of these are critical points. Critical points are at x equals 0, 2, and 4. Because what's the definition of a critical point? Where the derivative is 0. Where the derivative is 0. And when you're looking at it graphically, that means that the derivative crosses the x-axis. So we've got 3 places that we have critical points. Very good. That's easy to see from the graph there, okay? So what about inflection points?
There with the derivative 0, so it's going to be 1 and 3, or kind of near 3.
Right. Inflection points. Okay. Now, for inflection points, remember your definitions where the second derivative is 0 or undefined and the concavity changes. So we've got 1 and 3 as potential inflection points, okay? We don't know that they are inflection points until we determine something about the concavity of it, truthfully, okay? But we know that much. Does everybody agree with that? All right. How do we determine where the function is increasing and decreasing?
Where the second derivative is increasing. Wait, the function?
The function. Because that's what we're asking for here. It's not clearly worded. Where is the function increasing at? What has to be true for the function to be increasing? What has to? It is. What do you mean by it? Yes, okay. So f is increasing wherever the first derivative is greater than 0. That means that f prime is greater than 0. Well, where is f prime greater than 0? How can we determine that from this? Okay. All right. How do you know it's at those places? You're right, but how do you know? What in the graph tells you that? Where the function f or where the function f prime? Okay. So for f prime to be greater than 0, graphically, that means that f prime is above the x-axis. So this area here and this area here. So f is increasing, which is the same thing as f prime is greater than 0. That's from 0 to 2, 0 to 2, and 4 to infinity we'll put because we're going to make the assumption that it continues in that same path there. We don't have anything to say otherwise. So 0 to 2 and 4 to infinity. Now, for some of us, this might be an easier thing to do, actually, to figure out the increasing and decreasing. Something I like to do is I go ahead and I am going to make a sign line for f prime. Okay? So you remember sign lines, we've done those oodles and oodles of times. If I give you an algebraic expression as a function, you're going to find the derivative, set it equal to 0, and then determine where it's positive and negative. Okay, so where is our derivative equal to 0? At our critical points, which are at 0, 2, and 4. Okay, so once we do those, 0, 2, and 4, now that means since those are places where the derivative is 0, everywhere else the derivative is either positive or negative. So when we look at f prime before 0, the graph of f prime is below the x-axis, which tells us that it is negative. F prime is negative there. If we look at it between 0 and 2, the graph is above the x-axis, which means that it's positive. From 2 to 4, the graph is below the x-axis, so it's negative. And from 4 on, the graph is above the x-axis. So we can look at the sign line, and to me, this is what I'm more comfortable looking at is sign lines. So I can look at the sign lines and determine that the function is increasing from 0 to 2 and 4 to infinity. Where is the function decreasing? Again, looking at the sign line, how can I tell that? All right, where it's negative, so that looks like it's from negative infinity to 0 and 2 to 4. Okay, so we figured out where the function's increasing. We know where the function's decreasing. We know where, can we determine, what else can we determine from looking at the sign line? Can we determine max and mins from the sign lines? Okay. Is 0 a max or a min? Or neither. 0 is a min. So for minima, we have x equals 0. What about for max? What about at 2? What is 2? Because the derivative is positive before 2, it's negative after 2. So it's a max. And at 4, the derivative is negative before 4. The derivative is positive after 4. So 4 is a min.
Does that match up with the graph we're doing?
What do you mean by the graph that we're doing? Okay. Now this original graph is the derivative. So the derivative was negative and then it was positive, so that should be a maximum there. See, it's not going to look like this graph because remember, we'll figure out what f looks like here in just a moment, hopefully. But no, it's not going to. We don't have a maximum at 2 and a minimum at 0 and 4 on the graph, because this is the derivative that we're looking at the graph of. So we figured out the maxima and the minima from that. We know where the function f is increasing. We know where the function is decreasing. Now, can we do the same thing that we did for f prime for f double prime? By that I mean, can we come in here and can we make a sign line for f double prime? Well, we already talked about where the second derivative was. We've got potential inflection points at 1 and 3 because the second derivative is 0 at those two places that I just circled in black. So we can go and put those on our graph, 1, 3, just like before. That means before 1, either the second derivative is positive or negative. How do we tell whether the second derivative is positive or negative? Anyone? By looking at this, how do I tell?
Where it's decreasing is negative.
Okay, where it being f prime, wherever f prime is decreasing, the second derivative is negative. What does it mean for f prime to be decreasing? It's got a negative slope. So if we look in here, the slope of our graph all the way up to this point here that we've got circled around 1, what would you say about the slope from everywhere up and to 1? Is that slope positive or negative? It's positive. So that tells us then that the second derivative is positive before 1. What about from 1 to 3? Again, if we come in here and we try to draw our slope in, that slope is going down, so that slope is negative. So that tells us that the second derivative is negative from 1 to 3. And what happens from 3 on? The slope is positive. And remember, when I say slope there, I'm talking actually about the second derivative. It's the slope of f prime. This is where it gets confusing to you, okay? The slope of f prime. We're looking at the second derivative by looking at the slope of f prime. So now we know, remember before we said that 1 and 3 were potentially inflection points. Is 1 an inflection point? Is 3 an inflection point? They are. So we know now for sure that we have inflection points at x equals 1 and x equals 3. What does the second derivative being positive tell you about the function? Concave up. So we know that it is concave up from negative infinity all the way to 1. What do we know about from 1 to 3? It's concave which way? Down from 1 to 3. And what about from 3 on? It is concave up 3 to infinity. Okay? So we have gathered together an awful lot of information about this function from just that. Can you draw the function now? Can you sketch out what the function would look like? Let's see. I'm going to take this. Actually, I'm going to take... I'm not going to do that. I'm going to take that, copy it down the page here. All right. Now we've got the first derivative and the second derivative sign lines here. I think we can sketch out basically what this graph looks like now. Where do you think we ought to start?
Critical point.
Okay. Where are our critical points at?
What is the first derivative
So that's at 0, at 2, and 4. So what do we know? We know we've got critical points at 0, at 2, and at 4. Right. Okay, so we know that it is a minimum right here, right? So that means that the function's got to be doing something like this around it. Would you agree? We know it's a maximum at 2, so it's got to be doing something like that. We know it's a minimum at 4, it's got to be doing something like that. Now, do we know that this point is actually, the x equals 0 is right here on the y-axis at about 1 here? No. It could be anywhere on the y-axis there. Do we know that this point at 2 is above the point at 0? Mm-hmm.
The point, we know it's above the point at 0 because, yes.
Yes, okay. Why?
Because if it was below it, then the function would have to go down to reach it. So.
Right, so because it's a max, it's got to be higher than that one there. Yes, sir. Yes, sir. So we know the function is going to look basically like this, in that we've got a min, a max, a min. But they could be stretched out dramatically. This minimum point could be way down here at negative 700 somewhere, and this maximum could be at negative 35. We don't know where it is on here, but we know it has to look basically like that so far. Well, now let's look at our concavity. It says it has to be, so just based on what I've drawn in here so far, I think we could probably make the argument that the graph has to look something like this. Would you agree? Now, now use our second derivative to see if we think it really does look like that. The second derivative says that it is concave up from negative infinity all the way to 1. What does it mean to be concave up?
It means that.
Yes, it looks like a U. It holds water, okay? So this looks kind of like a U, and along in here about at 1, it looks like it starts turning over. Does that make sense? Now, we can't say exactly by the graph, but it looks like it starts turning over. It's concave down from 1 to 3. So again, about 3, concave down means it doesn't hold water. That kind of meets that criteria. And from 3 on, it's concave up. That looks like it would hold water. So our graph could look something like that. But remember, it could be stretched vertically dramatically from that. I mean, it doesn't have to look like that sideways W. It could be a real long W. But that's the basic gist of what that function should look like. And we got all of that information by looking at the derivative and finding information about it. Yes, sir?
The intervals for the derivative is positive and negative with that is then increasing and decreasing, right?
That's right. Let me read that right. Intervals where the derivative is positive. The derivative is positive is just another way of saying f is increasing. Okay? Now, you're really going to have to work to get all these things straight in your mind and think about those. Because sometimes we're going to say the derivative is positive. You've got to relate that to mean that f is increasing. Sometimes we're going to say f is increasing. You've got to be able to relate that to saying that the derivative is positive on that, okay? Yes, this part right here is asking the same thing as where the function is increasing and decreasing.
Sure.
All of those mean the same thing. Good morning.
Good morning.
How was your breakfast?
It was good.
Good. So, all of that information we got just from that one little graph. Does that amaze you maybe a little bit? I mean, just from one little picture, we're able to glean all of this information about this function that we don't really know anything about. Okay? Take this down the hall to physics. Don't y'all love it when I keep bringing up physics all the time? If you've got the velocity of something, if you could figure out what the velocity looks like, you can make a great path make a pretty good judgment call about what the position would look like in any given place. Okay, because you know where it's going fast, where it's going slow. So a lot of good information we can get just by looking at the derivative. Let's take another one. Here's f prime. Same directions as before. So I want to give you about 5 minutes or so, maybe talk with a neighbor if you want to, and see if you can determine all of that information. Where are the critical points? Where are the inflection points? Where is the function increasing and decreasing? Where is the function concave up, concave down? Where is the derivative positive and negative? And where are the maxima and minima? So I'm going to give you 5 or so minutes to see if you can figure that out and come up with some answers there. I've written out the steps that I would kind of follow if I were you. I think it's easier if you can approach it that way. Okay, this is the graph of f prime. Okay, we want to know, and all of these questions are talking about f, the critical points of f. The critical points of f are where the derivative equals 0. The derivative, we've got a graph of the derivative. The derivative equals 0 wherever it crosses the x-axis with the graph. So we're looking for where it crosses the x-axis, 0 and 3. 1 is where the derivative has a derivative of 0. So 1 is a possible inflection point.
What are the qualifications of inflection point?
The derivative is 0. Second derivative is 0. Second derivative is undefined. Or second derivative is 0 or undefined, and the concavity has to change. So that's the reason I put a question mark there by inflection points, because we don't know it's an inflection point until we research it a little bit more. Ah, yes, it would. You are right. Because right there it would be. Well, it qualifies as a possible inflection point. So just looking at the graph, let's talk back through it. The critical points are where f prime is 0. And by looking at the graph, we can know that f prime is 0 wherever it crosses the x-axis or touches the x-axis. That's at 0 and 3. So that was our first thing that we did, is we found that where x is 0 and x is 3, that's where we have critical points. Then how do we tell about the derivative being positive or negative? Is it above or below the x-axis? The derivative before 0 is below the x-axis, so we transfer that to our sign line as negative. That means the first derivative is 0 when x is less than 0. From 0 to 3, the graph is above the x-axis. The graph of f prime is above the x-axis, so we can say that it is a positive first derivative. And from 3 on, the graph is also above the x-axis, so it's a positive number. So that's how we get our sign line written there in red for our critical points. Now, our inflection points are where, or possible inflection points, are where the second derivative is 0. Second derivative is 0, we can determine by looking at the graph, where does this graph, the graph of f prime, have a slope of 0, or if its slope is undefined. It has a slope of 0 at 1. It has a slope of 0 at 3. So we have those as possible inflection points. How do we determine if the second derivative is positive or negative around these places? If you remember, that's looking at the slope of the first derivative. So if we look before the number 1 at our graph, if we were to try to draw the slope in here, the slope of the graph is going up. The slope of the first derivative is going up, so that means the second derivative is positive before x equals 1. Another way to look at that is, where is the first derivative increasing? If the first derivative is increasing, going up, then it's positive. The first derivative is going up, it's increasing, so the slope is positive. From 1 to 3, again, if we look at those in there, the first derivative is going down. The first derivative has a slope negative, so the second derivative is negative. So is 1 an inflection point? Because it goes from positive to negative. Very good. All right, at 3, the first derivative, after 3, we've got, again, the second derivative is going up, so it's positive. So is 3 an inflection point? All right, so now that we've got our two sign lines, we should be able to answer all the questions that we were asked simply by looking at our two sign lines here. So, what are the answers to our questions here? Our critical points are 0 and 3. Inflection points are 1 and 3. Where is f? What was the next question? Where is f increasing? What does it mean for f to be increasing? To be positive, what's positive? For the first derivative to be positive. You said 0 to infinity?
And then you could where x does not equal 3.
0 to infinity and x is not equal to 3. That's one way to write it. A better way to write that would be it's increasing from 0 to 3 and 3 to infinity. That's what I would rather see you write, because it's too easy to forget the other. It's not increasing at 3. At 3, it's flatten out. We've got to figure out what that looks like here in a moment. But it's not increasing at 3. It's increasing from 0 to 3 and 3 to infinity. Where is f decreasing? Where the first derivative is negative, and that is from negative infinity to 0. All right? Where is the function concave up and concave down? Okay? F is concave up. How do we determine concavity for our function? Second derivative. So F is concave up where the second derivative is what? Anybody remember? Concave up? Yes, concave up means that the second derivative is positive. Okay, so it's from 0 to 1, infinity, negative infinity to 1, and 3 to infinity. And then it's concave down from 0 to 3. Or no, it's 1 in all of those places, isn't it? 1 to 3. We were asked to find the maxima. All right, where's the intervals where the derivative is positive and negative? We said that's the same thing as f increasing and decreasing, right? So we can say here that means also f prime is greater than 0. So that answers that question. Where are our maxima and minima? Do we have any maxima?
No.
No maxima. Do we have any minima? At? Yep. At 0, right? We have a min at x equals 0 because the first derivative goes from being negative to positive, so 0 is a minimum. Now, what is this graph going to look like? Let's find a different color. What is this graph going to look like here? If we're going to sketch out this graph, what do you think it's going to look like? You can either use what I've just written over here in green, or you can go back to your sign lines. It's all the same information there. We know at 0, we have a minimum, okay? We don't know where that minima is at, but we know we have a minima. I'm going to pick a funny, different color, kind of, sort of. It might be a nice burgundy there. So let's put a minima right there. And just like we said before, it could be anywhere on the y-axis. It doesn't really matter where. We know that's a minima, so that means that the function has to be doing something like that there. What about at 3? What has to happen? It flattens out, but so we know that after 0 it's going up, and then over here at 3 it gets flat for a second and then starts right back up, something like that. Okay, so we've drawn that based on our red right here. Do our inflection points agree with that? Is it concave upward from negative infinity to 1? Concave up. Again, it's kind of hard to decide, but somewhere in there it changes at about 1. So it's concave up. Is it concave down from 1 to 3? Again, it is. Is it concave up from 3 on? It is. Now, it could be stretched vertically, but it's not going to be stretched out horizontally any from there. So we've got some idea of what this function would look like based on that right there. I would also recommend, because do you recognize this as a little bit of maybe a couple of FRQs you've had before? We had where you had to sketch a graph. Y'all remember the ugly graph that said, yeah, it does something like this. You know, this is the type thing that you'll see in FRQs, but it's good information to be able to glean off. I would encourage you to go back and look, does what I wrote in green over here agree with the graph everywhere? Do I have critical points at 0 and 3? Yes. Do I have inflection points at 1 and 3? Yes. Is F increasing from 0 to 3? F is going up, yes. From 3 to infinity, yes, it's going up. Is it decreasing? Yes. If it does, then I'm pretty sure that everything's got to match up there. If it doesn't, then I've done something wrong. Okay? Very good. Is this easy or hard? Okay.
What is the third derivative?
I have no earthly idea. I mean, we've never gotten down to that level. Yes. I mean, it tells you something, but it's not anything that's, up through all the calculus I took, it didn't do anything for me. So you'll have to go further than me. All right, now, shift gears a little bit. Here's a function, f. Graph the derivative and graph the second derivative. Yeah. Sorry about that. Here's the function. Graph the derivative and graph the second derivative. How do you even begin?
Well, the slope seems to be negative.
Where?
The slope seems to be lessening.
Okay. How do you think the best way to start this?
Find the critical point.
Okay. Where's the critical point of f? Right up here. We've got a critical point. So I'm going to graph, so that means I know that f prime is 0 right there. Agreed? I'm going to do my f prime in blue. So that means, do I have any other critical points of f? No, because the derivative never looks to be 0 anywhere else. So that means after this point, from -1 on, is the derivative positive or negative? If I were to look at the derivative of f, if I were to come in here and look at this, describe that derivative in here, positive or negative? Negative. So that means it is, how do I graph negative? Below the x-axis, okay? So it's going to be down here. All right? Now, do I know that it looks like that line? Could it kind of curve up or anything there? We don't really know yet, but we know it has to be negative down there. We'll kind of save the rest of it there. How can we determine if it's just a straight line down here or if it's going to curve back up somewhere? Let's look at the magnitude of the derivative. The further I get away from -1, the more positive I get. What do you see the derivative doing? The more positive I get, the further to the right I get. Would you say that the slope in here might be like a -1, but the further down I go, the magnitude of this, meaning the number part, not the negative sign, the number part is getting bigger and bigger. It's -2, -3, because this thing's just getting steeper and steeper. So that indicates that the slope is going to continue to go down at some rate here. So the slope is going to be negative in there. What about numbers on the other side? They're all positive, and the closer I am up here to this -1, the closer the slopes are to 0. The further back I go, the higher they get. So that would indicate to us that the line is that it's going to look something like this. So that's what we would guess that our slope's going to look like. What's another reason we think our slope should look like that? Exactly. The function itself looks like it's x squared. So then if the function is x squared, we would expect the derivative to be 2x. Or if the function is 6x squared, we'd expect it to be 12x. But nonetheless, we'd expect the derivative to be a line. So that's what we've got there. Now, how do we draw the second derivative? Good question. Is it a dot or is it a line? It's a horizontal line. Why is it a horizontal line? Okay. Again, thinking about this, if this is 2x, then the derivative is just 2, so it would just be a horizontal line. Okay. Is it positive or negative? Negative. How do you know that? Because the slope of this blue line is negative. How about looking at the function? How do you know looking at the function that the second derivative is negative? It's concave down. So we can propose that the second derivative would be a horizontal line in here. Now, in both of these cases, do we know definitively that f double prime is negative 1.5? No, we just know it's negative. It might be negative 3, it might be negative 7. Do we know that this blue line is sloped like this? It could be much flatter, it could be much steeper. We don't know any specifics, but we're just sketching. We're giving you a rough idea of what this thing's going to look like. So this is skills that we are developing now and things that we have to continue working on. So look at this graph. I'll give you a couple of minutes to talk about it. Here's the F. Graph F prime and F double prime. Go. What do you think F is? It's probably a cubic. So then, hopefully from that, that'll give you some ideas. So if we go back and look at the first derivative, where's the first derivative equal to 0? At negative 2. All right. So that's the only place it's equal to 0. So the first derivative after negative 2 is positive. So that means it's going up. Is it going up in a straight line? Because it's almost 0 here, and then it starts getting a little steeper, and then it starts getting much steeper. So I think since it's curved there, we can kind of say it probably is not going in a straight line there. What about on the other side of negative 2? It's also positive, isn't it? So it's a positive number over there as well. And again, way out to negative 3, negative 4, negative 5, those numbers are extremely positive. And the closer we get to negative 2, they're getting closer and closer to 0. So we think our derivative is probably going to look something like this for our first derivative. Does that make sense? All right, then what about our second derivative? Again, I'd start off the same place. Where's the second derivative equal to 0? The same place here, right? Negative 2. All right, now remember the second derivative is the first derivative of the first derivative. The second derivative is the first derivative of the first derivative. So I'm just going to look at the blue line and take the derivative of it. After negative 2, the derivative is a positive number, and it starts off at 0, and it gets more positive as I go along. Before negative 2, the derivative is negative, and it is more negative as I go away. Now, if this were x cubed to begin with, if f were x cubed, that would be correct. It'd be x squared and then x. If this were x to the 5th to begin with, then it would be x to the 3rd. So the green line wouldn't be exactly right if this is an x to the 5th in here. But that's a general idea of it, of what it would look like. it might be a little bit flatter in here. Our second derivative might actually look more like this than like a straight line. If the black line, if the original were x to the fifth. But we don't have enough information really to determine what exactly it looks like. But this is a good sketch of it. This is about all I'm looking for out of it there, okay? If you can sketch out that much, I'm not trying to trick you there. That's all I want you to be able to do. All right. Let's see how many more problems we've got. 1, 2, 3, 4, 5. Oh, 1, 2, 3, 4, 5, 6. Wow, I went crazy today. 8, 9, 10. Were any of these homework problems? Jeez, I think I went crazy. Did I really give you all of those? Let's see. I think I'm doing some of your homework right now. That's what I'm afraid of. No, it's 28. Oh, my goodness. No, I'm not doing any of your homework. Okay, but we are going to talk about this a little bit tomorrow, so that's okay. Let's look at one more problem here. We'll talk about it tomorrow if we need to. Take that F, sketch F prime and F double prime. Take that F right there, sketch F prime and F double prime from it. You probably can come up with some idea of what the F is already. So that should give you a little bit of a hint of what F double prime should look like, or F prime and F double prime should look like. Now that I look at this, I think we've done this problem before. All right, looking at F, where is the derivative equal to 0? The derivative of F is equal to 0 here at pi over 2 and at 3 pi over 2. So I know those 2 points are on my graph. Draw them in there. Now let's talk about what's happening at other places. Maybe what's happening before pi over 2. the function is going up. That means that the derivative is positive. That means that our function has to be, that our derivative has to be positive before pi over 2. So it's going to look something like this probably. It could be a straight line, but we don't have anything that really says it's straight, so I'm going to give it a little bit of a curve. Okay, what's happening to the function from pi over 2 to 3 pi over 2? The function's going down. It's decreasing. That means that the first derivative is negative. But what we've got to remember is that at 3 pi over 2, it's back to being 0. So the function is not going to just continue going down. It's got to actually turn around and start coming back up somewhere. It's got to go down, but it's got to come back up to 0. Because if you look at the graph of f, do you see that along right in here, do you see that as an inflection point? So that means that that first derivative's got to bottom out somewhere around in there. So that's kind of what we see there. And what about from 3 pi over 2 on? The function is increasing. That means the derivative is greater than 0, so that means the function's going up. And again, we don't have anything that says it's going straight or curved. We're going to guess it's going curved because this kind of looks like a sine-cosine curve.
Well, don't we know it's curved because
we know it's curved because
we don't know. Okay.
we know it's kind of curved because, again, if we look, that probably looks like an inflection point in there. So that should mean that what happens? That should mean that this graph kind of gets to a flat spot right along in here somewhere. So that's just a rough idea of what this is going to look like. And now we could even go as far as saying back here, that's kind of looking like an inflection point here because there's a little bit of a curve starting to it. So we expect it to look something like this for the first derivative. Now, assuming that those 3 points that we colored in green are actual critical points, are actual inflection points, then that means that the second derivative has to be 0 at these 3 places here. Does that agree with what we've drawn for our blue? Where is the derivative of the blue equal to 0? Well, it's definitely equal to 0 right here. And these two flattened out appear to be flattening out so that they are back to 0 there. Again, we're kind of using some intuition because we think this looks like the sine and cosine curve. All right, well now, what about f from between these first 2 green points? F is concave down, so that means that the second derivative is negative in there. What about f prime? F prime is going down in there, which means that the second derivative is negative. So we would expect the graph to do something like this. It's going to be negative, but we know it's got to come back up to being 0 at that point there, which we believe to be pi. All right, well, let's talk about f between this point here, pi, and 2 pi over here, these 2 green points. It's concave up. That means that the second derivative is positive. If we talk about the first derivative is increasing from this point right here, pi, all the way up. So that means that the derivative of the first derivative is positive. So it has to be going up, but again, we know it has to come back down because it's 0 here. So we get something that looks kind of like the green there. And if we took the derivative of it, we would get something else. So we could just take oodles and noodles of derivatives there, continuing on. Get a good, somewhat of a feel for what to do with these? Would this qualify as hard? Okay. Now, I would recommend that you go ahead and start working some on the homework because it's going to be very similar to what we have done, I think, all the way through. We'll look at a couple of more problems on this tomorrow, but we're also going to talk about L'Hopital tomorrow so we can get all of the teaching done so y'all can use your time wisely in there. So nothing is due tonight. You can work on FRQs, you can work on this homework